Okay, welcome to another session of our reading group on the assumptions of physics. As usual, I should remember to put the link in the chat. There we go. And I'll recap what we did last time. So let's share. Actually, everything is completely new today. We are going to look at the directional degree of freedom. So there is basically nothing to recap. And share. And there we are. Okay, so Artem, would you like to start?
Yes, sure. So, directional degree of freedom. When recovering the structure of phase space, we only relied on the premise that Qi defined the units. We are now going to use that premise to define a directional degree of freedom. That is, a degree of freedom that identifies a direction in space. We will see that since a degree of freedom must be composed of two variables, the only directional degree of freedoms that are possible are those in three-dimensional space.
Yes. So there is this crucial mathematical fact that the only sphere that it's a symplectic space that it means that allows these conjugate pairs is the two sphere, so the surface of a sphere in three dimension. And I've no idea why. This is not well known in physics. Like even people that work in the foundations of physics are completely unaware of this, even though they might know that there is such a thing as a symplectic structure in both classical mechanics and quantum mechanics. And this is the reason why essentially we can justify having three-dimensional space, and we can also justify the fact that quantum mechanics uses complex numbers. It's because the block ball is a sphere. The only sphere that would be symplectic is the one in three dimension. Therefore, you have complex numbers and not real numbers and so on. So this is what you're going to use here. And the main thing is to justify why an independent degree of freedom is actually a sphere. Once you have justified that an independent degree of freedom for a direction has to be a sphere, then you have that the only possible one is the one in three dimension.
Magnetic dipole. Spatial and temporal degrees of freedom are fundamental importance given that every object must be located in space and time. We now want to focus our attention on a different type of degree of freedom, one that captures a direction in space. In general, objects are not completely spherically symmetric and can be distinguished by their orientation. This is also true for fundamental particles, as their intrinsic angular momentum, their spin, gives them an orientation that can be detected and manipulated through magnetic forces.
To study this case, let's consider a magnetic dipole. The magnetic moment μi can be written as μi equals, so we have the charge, the mass, and the angular momentum. Oh, okay, that's written there. The Hamiltonian for the magnetic dipole subjected to a magnetic field is given by minus the product of the magnetic moment and the magnetic field. What would be the word for the
Yeah, magnetic field, yes.
Okay. I know that like in Ukrainian we say something of the magnetic field, but maybe not in English. Okay. To write the equations of motion, we need to know what the conjugate variables of the angular momentum are, or equivalently the form omega AB or the Poisson brackets. Typically, one is given the Poisson brackets, therefore we will start from those. They are, and we have so we have the three different indices, and we have the Levi-Civita symbol.
Right. So if I and j and k are x, y, and z, you would have the Poisson bracket between Lx and Ly is equal to z. And then you use the cyclical, so y, z, x, and z, x, y.
In Hamiltonian mechanics, we can write the evolution of any quantity f of Q and P as, yeah, so we have the time derivative of f, then we rewrite that via the chain rule, right? And then we rewrite the derivatives of position and momentum using Hamilton's equation, and then we see that it's just the Poisson bracket with the Hamiltonian.
Yeah.
Therefore, we have, now we write that for the angular momentum. Okay.
So you have the component of the angular momentum with the Poisson bracket with respect to the Hamiltonian. So we just substitute the Hamiltonian, and the Poisson bracket is linear, so everything that does not depend on L goes out. And now you just have the Poisson bracket between L, the other components, and with the J contracted with this and the I free. And now the two components, you get the one with the richly distributed tensor. So this is basically the vector product of the two, because the only free thing is going to be the perpendicular, right? And those two are going to be the sort of you have J and K define a plane, and the free component is the perpendicular to that plane. So, there you go. I have it here. So now this is just the cross product, and so you have the derivative in L is equal minus a constant to the cross product between the magnetic field and the angular momentum, the magnetic dipole. Yes.
And then, without loss of generality, we can assume that the magnetic field is oriented along the z-axis, and we just write that for the write out the components, right?
Right. So you have the z component, since we are oriented with the z-axis, is going to be 0. The L component, the rate of change in the x component, is equal to the magnitude in the y component times the magnitude of the field. So the more the field, the stronger the field, the more the change, and also the bigger component in L in y is going to give you a bigger change. And for the y, on the y component, you have minus the component in x. So the idea is that this is going to oscillate, right? It's you have the two variables that are coupled with each other in sort of one proportional and one negatively proportional.
If we integrate, assuming Li equals some Li naught at time t0, we have, and we get that oscillation.
The precession, yeah.
Which gives us the Larmor precession of the magnetic moment. This is clearly a Hamiltonian system. It obeys Hamilton's equations, but it seems to have three variables, the components of Li instead of an even number. Shouldn't we have conjugate pairs?
Now that the norm L of the vector is a constant of motion, only the angle changes. You can then write Li equals L times Ni, where Ni is a unit vector. This state space can be understood as the space of all possible vectors with the same magnitude, which is the surface of a two-sphere. The size of an area A over the surface of a sphere of radius r can be measured using the solid angle, sigma equals A over r squared, which is already a unit independent quantity. The infinitesimal solid angle can be written in terms of the polar angle phi and the azimuthal angle theta. So d sigma equals sine of phi, d phi, d theta. The two variables are not conjugate, as the area is not simply the product of the differentials. However, we can write d sigma equals minus d cosine phi d theta. Right? The cosine phi is simply the component along the z direction, while theta is the angle on the xy plane. Changing the orientation of the solid angle and relabeling for clarity theta equals theta xy, we get d sigma equals d and z, d theta xy.
And
Which
by
means
the
that
way, it's omega, not sigma.
this is omega, yeah, right? Sorry, I
That's
just
okay,
read.
don't worry.
Yeah, d omega, right. Which means that the angle on a plane and the component orthogonal to the plane are conjugate. If we pick the variable theta x, y and the coordinate q and lz as the conjugate p, we have two variables with the right geometric relationship and with the right units. Right, so theta as q and lz as p, okay. Therefore, we have this. So this is.
So basically what we're doing is trying to find what the conjugate variables are, right? And the conjugate variables are the angle and the component on the perpendicular plane, on the perpendicular of the plane where the angle is defined. And so you get the right commutation relationship. Now the commutation relationship between this is a 1 in the same way that the Poisson bracket between position and momentum is 1. And now what you do is write the component based on LZ and the angle, knowing that the total angular momentum is a fixed quantity.
Right.
And then what you can do is recover now the Poisson brackets for the components, knowing that you can express Lx, Ly, and Z based on the conjugate quantities. And
Did
now
we, sorry, did we at some point like switch, did theta xy, is theta xy like our polar angle now? Or I missed this.
It should be so there are two angles, right? There is the polar angle, right, and
Yeah.
the azimuthal angle. So the polar angle is sort of the inclination on the x direction, and the theta is on the xy plane. Right?
This is okay. This is just this is the mathematician convention or whatever.
Yes,
Okay,
yes.
I'm used
Like
to it
you
being the
always
other
have
way.
to. Right, so that's why I wrote it specifically here. There are the two conventions that are exactly switching the two things. So, and typically when you have spin, the angle is theta. So I use that convention. I don't even know if physicists are consistent. Yeah, they say that there is the mathematician and the physicist convention, but I don't even know if people are completely consistent. But yeah, so that's why I write xy, so that this is clearly the angle along the xy plane. And then once we have this, I don't think we're going to go through this in detail, but then it becomes just a matter of applying the formula, which is the nice thing. So now you have the Poisson bracket between the two things, and the conjugate variables now are not q and p, are theta xy and lz, and you just do the derivatives. So here you have a derivative on one side and the derivative on the other side, and you just you just go and do the math. So when you are deriving with respect to the angle, you're basically switching cosine to sines, and when you're deriving with respect to LZ, you get the 1 over the square root and all that. And the cute things is that when you do that, the sign are gonna get squared, right? And you get the correct expressions. Like everything factors in a nice way. And so you do that, and so instead of saying I start with Lx and y and z and have have Poisson brackets with respect to those, you can say I start with the conjugate pair, like I do for position and momentum, and then everything else is a function of those, and you recover the same thing.
Okay, we can verify that Hamilton's equations work as before. If the magnetic field is aligned along the z direction, it's the same Hamiltonian.
Right. So now it's even going to be easier, because what happens is if you make the derivative with respect to LZ, this is just a constant, right? And so the change of the angle is a constant, so you have a constant angular velocity. And the derivative with respect to the change in respect to LZ, since the Hamiltonian does not depend on the conjugate on theta xy, this is 0, and so the thing does not change.
Right,
so
then
you
you
can
integrate
set,
that, and yeah.
Yeah, so now you can set the initial condition for LZ. You can have that the angle is just a linear function of t, because and where this omega is basically this constant, and then you can write everything else using this relationship, right? You can just plug in the thetas and the LZ in terms of time, and you write things, and then at the end you can recollect the result, and you get the same thing. So this is just to make sure that everything works nicely, and it's I don't know. I always find it fun when the math sort of recombines itself, and you get the thing that you expect. So.
Well, I guess I can finish this. It's short. Let us sum up what we learned. Magnetic dipole is described by a single degree of freedom, where the conjugate variables are the angle on a plane and the component of the angular momentum perpendicular to the plane. The constant force does not correspond to constant angular acceleration, but to a constant angular velocity. Now the question is how and to what extent these can all be generalized.
Wouldn't maybe I spaced out a little. Wouldn't
Yeah,
it
yeah.
be shouldn't it be like when we align the axis properly, there's 1 degree of freedom.
Yeah. So you
Okay,
have the magnetic field
yeah.
that it's going to be aligned in some axis, and then the component on that axis remains the same, and the perpendicular component has a constant angular velocity.
Yeah, sure. Okay. So generalizing to directional quantities. The above treatment works without modification regardless of whether the magnetic dipole describes a small solenoid, a small rotating charge distribution, or the spin of a single particle. Spin was originally thought to be due to a rotational motion of a particle, hence the name. However, this would require, for example, an electron to be spinning at velocities that would exceed the speed of light. Therefore, this view is no longer favored. But if spin is not due to a rotation, why does it have the same properties as angular momentum? Is it a coincidence?
Let us call directional quantity a quantity Li defined only by a direction in space, meaning that the magnitude of the quantity norm of Li is equal L is fixed, an intrinsic feature of the object, while the direction can change. Magnetic dipole generated by either spin or rotating charge can be considered a directional quantity. The question now is whether the directional nature is enough to recover its properties.
If we want to keep track of a direction in space, the angle theta xy of the component of the direction on a plane is an actual variable to use. Therefore, theta xy is a natural choice for a unit variable. Because of the structure of phase space, we will have a conjugate quantity Lz that we call directional momentum. Given that a directional quantity is fully determined by a direction in space, the count of possible configurations is proportional to a solid angle. As we saw before in the context of a magnetic dipole, this means that the conjugate quantity Lz must be proportional to the component of the directional quantity perpendicular to the plane where theta xy is defined. Therefore, small lz equals k large LZ for some constant k.
Recall now that the product of conjugate quantities must always be in units of phase space. We already noted, in fact, that if a coordinate is dimensionless, then its conjugate must have dimensions of angular momentum. Therefore, directional momentum, big LZ, must have dimensions of an angular momentum, regardless of what the directional quantity little li is about. Thus, even if the directional quantity is not an amount of rotation defined by an angular momentum, we can still write little li equals k big Li, where the big Li is expressed in units of angular momentum. That is, a directional momentum Li arises naturally every time we have a directional quantity. In the case of a magnetic dipole, it is the gyromagnetic ratio, K equals mu I divided by Li equals Q onto M.
We want to stress that for a directional quantity, both variables, the directional momentum Lz along a given direction Z, and its angle theta xy on the perpendicular plane are effectively tracking a single quantity. This is different from what happens in a spatial degree of freedom, where the coordinate q determines position, while the conjugate p determines conjugate momentum, and therefore the velocity, which are different properties of the system. This fact tells us that a force acts differently in the two cases. A force for a spatial degree of freedom will in general affect momentum and therefore velocity, which means it will impart an acceleration on position. However, for a directional quantity, the only thing that can be changed is a direction. Therefore, a force can only impart a change in direction, a directional velocity. To sum up, a force over position will impart a constant spatial acceleration, while a force over a direction will impart a constant directional velocity.
This, I don't know about you, but it's something that I always found fascinating because it kind of breaks the symmetry. Like in terms of directions, the laws are not second order. So
For a rotating rigid body, the situation may seem different. We do have an angle and an angular velocity, and the angular momentum is the angular velocity times the moment of inertia, much like kinetic momentum is mass times velocity. Given that angular momentum is conserved, angular velocity is conserved, and a force needs to be used to change the angular velocity. Therefore, at first glance, the situation seems different from the magnetic dipole. On the other hand, we are dealing with an angular momentum in both cases. Therefore, the situation can't be that different.
The issue here is that there are two directions. One is the direction of the axis of rotation. The other is the orientation of the object on the plane of rotation. While the second one constantly changes, the first may be fixed. Note that the ability to discern the second assumes the ability to discern parts of the rigid body. If the object is too small with respect to our resolution, the orientation angle cannot be defined. On the other hand, even if we study the overall object, we would still be able to discern the direction and magnitude of the angular momentum by performing a rotation. In fact, if the rotation is performed along a direction different from the direction of the angular momentum, a torque will need to be applied to perform the rotation. The greater the angular momentum, the greater the torque. We are now in a case similar to the magnetic dipole, where a constant force is needed to impart a constant velocity.
We have seen that if we want to describe a directional quantity, and only a directional quantity with state variables, there's only one way to do it, and it will lead to a notion of directional momentum. Spin and angular momentum are, in our definition, two types of directional momentum. Is this the only way to do it? That is, why does a directional degree of freedom only include the directional quantity without the directional velocity?
Suppose we want to describe a particle in the sense of an infinitesimally small part of an object, which is not only characterized by a position, but also by a directional quantity. If we pick a specific time t, the position and direction at that particular time are independent variables in all senses. We can choose units independently. We can choose from all possible configurations of each variable. And the choice for one variable does not constrain the choice of another variable. It is true that we need to relate the direction identified by the directional variable to the reference frame used by the position coordinates. Yet we are not forced to choose a particular plane for the directional angle theta.
The situation between velocity and the directional velocity, however, is different. Contrast the following two cases. In the first, we are in an inertial frame with a particle at rest, whose directional quantity changes with a constant directional velocity. In the second, we are in a rotating frame with a particle at the center, whose directional quantity changes with a constant directional velocity. If we look only at the directional quantity, these two cases are indistinguishable. We need to know which frame we are in. Knowing the frame ultimately means knowing the definition of our spatial variables. That is, there is a definitional dependency between the spatial variables and the directional variables, which are, in the end, defined in space. We are free to choose the relationship between the variables at a specific time. To relate the directional quantity at different times, we must know how the spatial coordinates change in time. Therefore, the directional quantity is an independent quantity with respect to spatial degrees of freedom. The directional velocity is not. We reach the following insight. An independent directional degree of freedom must be restricted to a directional quantity.
We concluded that an independent directional degree of freedom only includes a directional quantity, so the structure we have for the magnetic dipole is an instance of a general structure. However, note how the directional quantity fits exactly in one degree of freedom. Is this necessary? That is, could we have a directional quantity that fits in more than one pair of conjugate quantities? In other words, is it possible to have directional quantities that break up into multiple independent degrees of freedom?
As we said before, identifying a direction in 3 dimensions is equivalent to identifying a point on a 2-sphere. If we had an n-dimensional space, a direction would correspond to a point on an n-1 sphere. That sphere will have to allow a description in terms of conjugate variables with a suitable form omega AB. It is a result of symplectic geometry that the 2-sphere is the only sphere that allows that structure. Therefore, another insight, an independent directional degree of freedom can only exist in a 3-dimensional space. I can just finish. In other words, 3-dimensional space is special as it is the only space that allows to talk about directions as forming an independent degree of freedom. This is yet another example of how simple, unassuming premises have significant consequences.
Okay, so let me go through the whole argument from start to finish. So first, we just look at how things are, from the physics, because we're doing reverse physics. So we look at how spatial direction works. We get the example for the magnetic dipole, and we basically see that you have a direction, and just the direction forms a set of variables on which you can write Hamiltonian, do Hamiltonian mechanics, write Hamiltonian, all of that. And then we can find that we can use the angle and the normal component to the plane of the angle to define conjugate quantity. So we have now two nice things, and that's sort of how it works for magnetic dipoles and angular momentum and so on, right? So we have that. And now we have to see whether that's the only thing that you can do. What you basically say, if you have any function that it's... okay, can you elaborate more? Question from the chat. What do you want me to elaborate more, Ian? Okay, I'll continue and then keep an eye on the chat. Okay, so now if I have a quantity that has, oh, there you go. Can you elaborate more on the comment about page 85? To sum up, a force over position will impart a constant spatial acceleration, while a force, yes. So this is what we find here, right? That if we have a Hamiltonian, right? Where is the Hamiltonian with, oh, I can have it here. If we have a Hamiltonian with a constant magnetic field, right? We're applying a constant magnetic field, we have a constant precession of the angular momentum. So if we have no magnetic field, the magnetic dipole remains where it is. It does not change, right? And if we apply an angular magnetic field, then we have a constant velocity, right? So this is where I was saying that this looks a little bit different from what you have in position and velocity, because in position and velocity, you know, when you have a constant force, right, you have a change in velocity, because one of the variables, like velocity, is a constant change in position. So if you fix velocity, then you have a constant change in position. But here we are fixing the direction of the angular of the magnetic dipole. It remains where it is, like it doesn't change. Like this is just again a factor of how, let's say, nature works. Like it's an experimental factor. This is what you see. And now we basically have to make sense of whether this is some kind of coincidence or if there is an underlying reason. And so the first thing that you say, okay, suppose that I have a directional quantity, right, and it's not an angular momentum. Would I still find an angular momentum? And the point is yes, because if I have a quantity, I will be able to have an angle in some direction. And the conjugate of that angle, just for the fact that units of phase space, right, has to be the same regardless of what directions of freedom, or what degree of freedom you have, then the conjugate quantity has to be an angular momentum. So even if your L is not at all about rotation and angular momentum and so on, still the conjugate quantity of the angle has to have the same units, right? And so really what you should think about the units of angular momentum is not really units of angular momentum, it's really units of phase space divided by a pure number, which in this case is the angle, right? Because also if you change the angle from radians to degrees, your conjugate quantity is going to change, right? So the definition of the units of this still depends, still influences the units of the other one. And so whenever now you have your original quantity little l, you can always find a constant that allows you to go from one quantity to the other, because this has to be proportional. And for example, in the case of the magnetic dipole, you find that k is actually a physical quantity, is the gyromagnetic ratio, right? So these things, regardless of what directional quantities you're going to have, you are going to have an angular momentum and a ratio between the quantity, the directional quantity that you're interested, and the angular momentum, the canonical variable that you're going to use to describe it in terms of Hamiltonian mechanics and the symplectic form. So once you've established that, whenever I have a direction, I can always express it into angles and angular momentum. Now the question becomes, why is it, let's go back to the idea, why is it that I have this constant direction when I'm applying no forces, and when I have a force, I have a constant velocity in that direction? And here we go and look at what happens with a rigid body, because in that case, the angular momentum itself is a direction, but it's expressing a rotation, right? So now you have the thing that is similar in mechanics, because you have the two quantities are the angle and the angular momentum, in the same way that you have the position and the velocity, right? And the angular momentum is the thing that gets conserved. If you move it around, if you let it stay, the angular momentum remains the same, but that angular momentum means that there is something rotated, right? So in the case where your direction is an actual angular momentum, right, then you do have something that it's rotating. But in the case where your directional quantity is like spin, like it's a directional quantity, is there something rotating? I don't really know, but it doesn't really matter. The fact, what you can do is that you have spin, right? And so now the question is, can we find the idea that if I just look at my rigid bodies as a whole thing, like without knowing what is the substructure, right? Can I find again the idea that my directional quantity, my angular momentum, is something that remains fixed if I'm not doing anything, and when I'm applying a force, I actually have a constant change, and the argument is that yes, it's exactly works in the same way, because angular momentum is going to be conserved. So if I want to put a force and I want to change it, I have to put a torque, and now the constant force is going to give me a constant torque, which is going to be a precession of the angular momentum. So if I do not know how to measure that angle, because I can't look at the substructure and I can't see that there are two particles that are rotating onto each other, I just see the thing as a whole system, then I can't measure the angles. I can only measure the direction, and I can apply a force to that direction of the angular momentum, and then I would have a constant torque. And so even in the mechanic case, when you look at your mechanical system as a whole without knowing what the parts are, the angular momentum will act as a single directional quantity that remains where it is if there is no force applies, and has a precession if there is a constant force. And now all of this is just telling you that in all the cases that we've studied, we have this property. And now the question is whether this is a coincidence or it's really a definitional property of what an independent degree of freedom must be. So does the independent degree of freedom must be just the direction? Or I could have an independent directional degree of freedom, which is the pair of direction and then velocities on that direction. And this is where there is this argument that I completely forgot that I had made, is that the direction you can define independently of the frame that you are in. But the velocity you cannot, because in the case that you are in a rotating frame, what you think is a constant, something that is remaining the same, is actually rotating in a non-rotating frame. So to be able to know what how your directional degree of freedom is moving, you need to know the spatial degree of freedom. And so the velocity of the directional quantity is not independent in terms of the definition of what your position and velocity are doing for the actual spatial degree of freedom. And so since those are not independent, they can't be defined independently. If you want the directional degree of freedom to be independent, then it must be only the direction. And once you say, okay, now the directional degree of freedom is only the direction, then you ask, well, could I have a direction that is made more of two variables? And then you can't, because you need this, the conjugate pairs can only exist for a two-sphere. And so this concludes, then you basically say, whenever I have an independent directional degree of freedom, I must have something that it's a point on a two-dimensional sphere. And so that tells you that the three direction in space, it's basically the only way that you would be able to define this. So it's a little bit intense in terms of the argument. So if there are questions, and I can try to explain it better.
Can you explain, like for example, we a lot of the time we work was say the phase space of multiple particles, and say we have 3n dimensional or 6n dimensional phase space. We can, what I'm trying to say, we can define the direction for each of the particles, and like what I'm trying to say, what is the thing that we have
So let's see if I can
Yeah,
interpret what you're trying to express. So you typically, so when you have n particles, right, you have three n variables. And for example, we are saying that each Q is independent from the rest and can define a different variables. But then in practice, like they all live in the same space. So it's not that these n variables, these triples of n variables are completely unrelated to each other. And the fact that they form independence degree of freedom just means that you could define each, let's say, the direction of of each particle with a different unit. So for one particle, you use a Cartesian frame. For another particle, you can use a Cartesian frame rotated. For yet another particle, you use a polar coordinates, right? And so in principle, means that at least in terms of the definition, you can go and change these things however you want, right? So I can change. I can make one particle in one describe one particle in one reference frame and describe the other particle in the other reference frame. If they're subjected to the same gravitational forces, right? Then of course I will have to express the forces differently depending on what frame I'm using. But in principle, you can do it. There is absolutely no problem in doing that. With the velocity of the directional degree of freedom, instead, that's not the case anymore. Because I need to know what is the relationship of those variables to be able to know what's going on. I don't need to know what is the relationship between, let's say, the one coordinate that I use for a particle and the one coordinate that I use for the other particles. As long as I can write the equation, I'm fine, and I can change I can make a coordinate transformation in which I change the units of only one particle and not the other. I have no idea if there would be any practical purposes of why one should do that, but in principle you can do it.
Yeah, maybe to refine my question, the question would be why can't we say imagine a single particle that lives in six-dimensional space that just has instead of one independent directional degree of freedom, it has two independent directional degrees of freedom or stuff like that. Which
that becomes a different structure. So that becomes the existence of a metric tensor, and you are able to do all of those things. Right, so in principle, if you had, let me think about it. So first of all, you could have a particle that in principle have two directional quantities. That's not a problem. The relationship between the fact that a directional quantity is sort of two angles and therefore in 3D, and the fact that the positions are paired into three elements is because you are able to create directional quantities out of these triples. Right, so the fact that you can take two particles that are each of them in some n-dimensional space, that we don't know what is the dimension at this point, and you can put them together and couple them in a way such that you now have angular momentum, you have an independent degree of freedom over those n directions, then the fact that you were able to do it must mean that those n directions had to be three. So you could imagine a case, that's just wild speculation, that the particles themselves live in a six-dimensional space, But then when you couple them together such that they have an independent, directional degree of freedom, that degree of freedom itself lives in a three-dimensional subspace of that six-dimensional thing.
Yeah, what I'm trying to say, does that really establish that it does establish that those triples are special, but I can imagine situations where we have another n-dimensional space, but if we want to have directional quantities in it, those will have to like relate to some three-dimensional subspace or stuff like that.
Right. So right now, I don't have an argument of why that can't happen or shouldn't happen and so on.
Okay, thank you.
Yeah, right now the only argument that I have is that if I have independent, also there, right? Note I repeat, the degree of freedom has to be independent. So you can imagine that I have something that is just not made of independent parts. But then the fact that it's not made of independent parts might be tricky because then how can I define and study it if it's, there are all other issues there. But technically, the argument just tells you if I have a directional quantity, that directional quantity just has to live in a three-dimensional space. That's it.
I mean, that's still an interesting fact because
Yes.
you
But you're right that we shouldn't like over generalize. Like we should understand what the argument is, right?
like because formally you can define a direction in any number of dimensions, but the fact that
right.
the directional quantities may make three the special number is interesting.
Right. So the issue is that while you can do that, then you're going to have trouble to define Hamiltonian evolution on top of that. That's kind of the point. Once you have a sphere that it's not three-dimensional, you don't have a symplectic structure and how we are going to define a Hamiltonian and your Poisson brackets and so on. Right? And it's the same thing in quantum mechanics, right? You need this, you need to be able to write the Hamiltonian, you need to have the commutators, and you need a symplectic structure somewhere. And in quantum mechanics, the space of, let's say, a two-state system is the two-dimensional projective space. It's like the projective line. And the projective line for a complex space is the Bloch sphere. And the Bloch sphere is symplectic because it's a two-dimensional sphere. If you were trying to do quantum mechanics with real numbers, then the corresponding projective space would be a circle. So a one-dimensional sphere. It's not symplectic. If you were trying to use quaternions, because you like quaternions, and trying to do quantum mechanics with quaternions, then the sphere would be four-dimensional. Again, it wouldn't be symplectic. So if you look at the projective space and you say, I want a projective space that is guaranteed to be symplectic, you need the projective space of a complex vector space. So there are a bunch of other arguments that can reuse the fact that the three-dimensional sphere is the only symplectic one. And again, now of course becomes, why is it that we have the symplectic, why do we need the symplectic structure? And we had the argument for that like the last couple of times. So you need the symplectic structure to be able to define a count of states for independent degrees of freedom. And Ian says, John Bytes did a nice talk about spin spaces on the YouTube Edinburgh Exploration series this week. I'll have to check that out. And I don't think we have time to start something new. And next week is going to be essentially Boxing Day, so I will be around, and I will be at a conference up until let's see. I think up until the 7th, so we might be able to meet next time either the 9th of January or the 16th. I guess we'll discuss on Discord, and I hope I'll remember to post something on the channel as well, so that people that follow through the channel can look at that as well. And if there are no other questions, we can stop.
They have a great weekend. Have great holidays. Thank you.
Yeah. Merry Christmas, everyone, then.
Yeah.
And a Happy New
Holidays.
Year to everybody.
Yeah.
See
Happy
you
New Year.
next year.
See you.
Bye-bye.
Bye.